Hello everyone, welcome back to Orbit Unknown. Today, we're diving into a truly fascinating topic that might completely change the way you see the world. Stay with us until the end, because what you're about to discover is surprising, mysterious, and incredibly interesting. So, let's begin today's amazing journey. Look up at the night sky on a clear evening, far from the city lights, and just stare. Really stare. What you are seeing is not decoration. Every single pinprick of light scattered across that darkness is a sun, a real, burning, nuclear sun. Some of them so enormous that the word large becomes almost meaningless when you try to describe them. That thought alone should stop you in your tracks. Because we talk about space constantly. We see the diagrams, we watch the documentaries, we nod along. But most of us have never truly let the scale sink in. Tonight, that changes. Start with our own sun. The one that rises every morning, gives you a sunburn, grows your food, and keeps every living thing on this planet alive. It feels close. It feels familiar. But familiar does not mean small. Our sun is 109 times wider than Earth. If you hollowed it out and started dropping planets inside it, you could fit over 1 million Earths before you ran out of room. It contains roughly 99.86% of all the mass in our entire solar system. Every planet, Jupiter, Saturn, all of them, plus every moon, every asteroid, every comet, every drifting rock floating out beyond Neptune, all of it together barely accounts for the leftover fraction. And here is the humbling part. By stellar standards, our sun is average, ordinary. The cosmic equivalent of a mid-sized sedan. Then there is Betelgeuse. If you know the constellation Orion, you have already seen it. That reddish star at his shoulder, glowing with an eerie warmth that makes it stand out even to the naked eye. It does not look like much from here. But what it actually is will rewire something in your brain if you let it. Betelgeuse has a diameter of approximately 1.4 billion kilometers. Our sun sits at around 1.4 million kilometers across. That is not a typo. Betelgeuse is roughly 1,000 times wider than our sun. 1,000. If you replaced our sun with Betelgeuse right now, it would not just fill the space where our sun sits. It would reach out and consume Mercury, then Venus, then Earth, then Mars, and it would still be expanding, stretching all the way toward the orbit of Jupiter. For planets, including the one you are standing on, swallowed entirely inside a single star, and that star would barely notice. So the question that should be burning in your mind right now is exactly this. Is that the ceiling? Is Betelgeuse the largest thing a star can become? And if not, what is? To get there, you first need to understand how stars are born, because the answer lives inside that process. Deep in the darkness between galaxies, vast clouds of hydrogen gas and cosmic dust drift through space. These clouds are invisible and cold and seem completely inert. But gravity never sleeps. Slowly, over millions of years, bits of that gas begin pulling on each other. The cloud starts to collapse. As more material falls inward, the pressure at the center builds. The temperature rises. It rises and rises through thousands of degrees, then millions, until the core reaches a threshold that fundamentally changes the nature of matter. Nuclear fusion ignites. Hydrogen atoms are crushed together so violently that they merge into helium, and that process releases an enormous flood of energy. Light, heat, pressure radiating outward in every direction. A star is born, and the instant that fire ignites, something extraordinary happens. Two forces go to war. Gravity is still crushing everything inward toward the core. But now the energy blasting outward from that nuclear furnace is pushing back with equal force. They meet. They balance. Neither one wins. The star holds its shape, locked in a perfect standoff between collapse and explosion, and in that balance, it burns steadily for billions of years. That equilibrium is not a coincidence. It is the defining feature of what a star is. Our sun has maintained that balance for nearly 5 billion years without breaking a sweat, and it has roughly 5 billion more ahead of it. A slow, steady burn, patient and ancient and stable. But Betelgeuse was never that patient, and here is why. When Betelgeuse formed, it started with 15 to 20 times more mass than our sun. That sounds impressive, and it is. But more mass is not always an advantage. More mass means more gravity pressing down on the core. More pressure means a hotter fire. A hotter fire burns through fuel at a reckless, almost violent rate. Think about two campfires, one built with a small bundle of sticks, the other built with an entire pile of logs stacked high. The bigger fire blazes brighter, burns hotter, and dies faster. Our sun will live for 10 billion years total. Betelgeuse burned through most of its fuel in just a few million. On a cosmic timeline, that is barely a moment. And when a massive star exhausts the fuel in its core, something happens that seems completely backwards. The core collapses and heats up, yes, but the outer layers of the star react in the opposite direction entirely. They expand. They push outward. The equilibrium that held the star together for millions of years breaks down, and the outer shells bloat to sizes the star never reached during its entire productive life. Betelgeuse is not large because it is powerful. Betelgeuse is large because it is dying. It is a star in its final chapter, swollen and radiant. Burning through its last reserves the way a candle flares brightest in the moment before it goes out. Astronomers believe it will eventually detonate in a supernova explosion so violent that it will be visible from Earth in the middle of the afternoon, shining like a second moon for months before fading into memory. So if Betelgeuse grew enormous because it was running out of time, that raises a far more fascinating question. How large can a star get when it is young and healthy and burning at full strength? Is there a hard limit somewhere? Does the universe itself draw a line? The answer is yes. Absolutely, definitively yes. And the name of that line will stick with you. It is called the Eddington Limit. And to understand what it means, you need to hold on to that image of the two forces in balance: gravity pulling inward, energy pushing outward. Now imagine a star that starts forming with not 15 times the mass of our Sun, but 100 times, 200 times. At that scale, something begins to go wrong in the most dramatic way possible. A star that massive burns so intensely produces such a staggering amount of light that the light itself becomes a physical problem. Here is something most people never think about. Light pushes things. Not metaphorically, literally. Light is made of photons, tiny packets of energy traveling at the fastest speed the universe allows. When a photon strikes a particle of gas, it transfers a tiny nudge of momentum to that particle. The same basic physics as a billiard ball tapping another one. A single photon delivering a single nudge is nothing, but a star radiating billions upon billions of photons every single second, all of them slamming into the gas layers of the star, creates a combined outward pressure that is very real and very powerful. Scientists call it radiation pressure, and it is real enough that engineers have actually designed spacecraft that use sunlight alone as propulsion, solar sails that ride the push of